Hi everyone, welcome to today's coding session. Today I'll be solving the word ladder problem using Python. I will explain the problem, its constraint, and the approach we'll be using. We will be using a breadth first search and a bidirectional breadth first search to find the shortest transformation sequence, and as I code, I'll explain each step in detail. Here is what the problem looks like, a sneak peek, and this is how we're going to approach finding the solution to it. I'm giving you this to show you the breadth first search involves us starting from level A, which would be level 0, then 1, then 2, and then 3. That's how we search for whatever problem we're trying to solve when we use breadth first search. Depth first search, on the other case, is using recursion. So we're going to go from level 0 to level 1 to level 3, and then all the way to level 4. In this case, depth first search will exceed our time limit, so we're not going to be able to use it. So we are given beginWord, which is here, and that's the starting word, which I showed you here, which in this case is going to be hit, and that's level 1. And we're also given endWord, which is our target word, which in our case is going to be here, which will be cog, or here, which will be cog. And then we're given a word list, which again is the word that's here on the ladder. That's our word list. And we need to determine the shortest sequence of word transformation where each transformation changes only one letter. The new word must exist in word list. The sequence starts with beginWord and ends at endWord. And here's a quick example. So we got beginWord, which is be hit, endWord being cog. First thing we want to do is the word cog inside the list? Yes, it is. It's right here. And then we're going to see, okay, from H, what is the next word that we can change starting from index 0? There's nothing that will be found here from A, B, Z, C. But here, if we change the I to O, we'll find one word. And that's now that we found hot, now we move on to the next level. So we went from level 1 to level 2, and we'll do the same process. We're going to change from H to D, and from dot, we're going to change G, and then from G, we're just going to change C. We found the word, and it took 5 levels to get there. In example 2, now here we're saying is endWord in the list. No, it isn't, so we're going to return 0. And that's the problem. So now that we understand the problem, let's think about the constraint. So the length of the beginWord, endWord, and each word in the word list is at least 1 character and at most 10 characters, which is what this is showing. All words have the same length, and the word list can contain up to 5,000 words, meaning we need an efficient searching strategy. beginWord, endWord, and the word list consists only of lowercase English words, so we only need to think about 26 possible letter substitution at each position. beginWord does not equal endWord ever. So we're going to be given beginWord here, and it does not equal endWord. So we don't need to worry about this situation. Okay, so since we are looking for the shortest transformation, breadth first search is the optimal approach in this case. Breadth first search ensures that we find the shortest path in an unweighted graph. And here's the algorithm. We're going to use a queue to store words at each level. Start with beginWord at level 1. Replace each character in the word with every letter from A through Z and check if it exists in the word list. And then if it matches the endWord, we'll return the level, which shows us the shortest path. If not, we're going to enqueue that word and then the new word and remove it from the word list to prevent revisiting. Again, this is how our level works. Level 0, 1, and 2, and that's breadth first search. And here, how this breadth first search works directly. So we'll go A, B, C, D, E, F, and that's how that goes. Depth first search being A, D, F, C, E, and B, which shows that we're going depth first, which is using recursion. Okay, now let me show you the code, or let me code it up. So first, we're going to do word set equal to the word list. We're going to turn it into a set in order to have O1 lookup. Then let's see if endWord is not in word set, we're going to return 0. And that's what we're trying to show here, that if the end word that we're looking for, in this case, for example, 2, we're looking for cog. We see that cog is not here, so we're going to return 0. And that's what we're doing here in this code right now. Now we're going to create a queue. And we're going to put beginWord there and 1 to show that we start off at level 1, which as you see here, level 1 being hit. So we're at level 1 right here, and hit is the first word initialized in queue. And we know now that the queue is not empty, so it's going to run, but when it is empty, this loop is going to end. And then word level equals queue. We're going to pop left. And here, the word queue already has something, which will be the begin word in level 1. We're going to remove it from the queue since it's first in, first out. And we're going to check for word next as well as level. So if the word is equal to end word, we're going to return the level. This means we found the word in end word, and we're going to return how many steps it took to get there. So we went from hit, hot, lot, log, all the way to cog, and it took 1, 2, 3, 4, 5 steps to get there. And that's what this is doing. And now here is what we're trying out, different range of combination. If the word does not exist that we created, if they do not equal each other. So this loop right here is looping through the index. It's going to loop through the index of the word. And this one right here is going to go through A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, X, Y, and Z. So this one right here is going to create different letter combination. And now is where we actually create the new word. So here, let's say we were given the word being equal to hit, which is our starting word. And let's say we have index equal to 0. And then let's say that we have word here 0. So that means this is going to be equal to the empty set, which we have, let's say, the word. And then chart, in this case, is going to be, let's say, the letter A. So since we got A, and now let's say this guy here, we're adding 0 plus 1, which is going to give us 1. So this is going to equal AIT. So when we have the whole word together, that's going to give you AIT. And as you can see, AIT is nowhere to be found here. And as we go through all the letter, all the way, let's say up to Z, we have zit, that's also not going to be found here. So index 0 is not going to be found. Now, if we were to change it, and now we are at index 1, and at index 1 here, again, we're going to have H. So all we're going to have here is H. Then we got chart, which will start at A, and here that's just going to be T, since we're going to have 1 plus 1, which is going to give us 2. So at 2, which should be 0, 1, 2, that gives us T. So now we have H, and now we don't have anything here, hat. And we're going to iterate through all the way till we find a word that is in the ladder, and we'll see that hot is in the ladder, and that's what we end up. That's what this part of the code is doing. So now if the new word is in word set, we're going to add this word or append it as a set to a new word, and we're going to increment the level. And at the same time, we're going to remove this word from word set. So this way we don't revisit the same word more than once. So each new time we find a new word combination that's inside here, we're going to, if it's inside the word set, we're going to append it to the queue. And this is going to be first in, first out. And then we're going to remove it from the ladder here. And the whole goal is to find the word cock. So we're building a path to our end word, one word at a time, as we change each letter. And now if we end up not finding the word, there is no path. Let's say there was no connection. Then we would say, okay, we cannot get to the word with the given word. And that being the case, we're going to return 0. We couldn't find a path. Okay, as we can see, it was accepted. And let's see. Okay, so it had 278 millisecond. It beats 59%, 13 megabytes. So it's fairly decent. It's not the greatest, but it's okay. Now let's walk you through an example, one specific example using breadth first search. So once we find out that the word is in the set, meaning once we do this bar, we create the list, we find out it's in the set, then we create a queue of the word itself, and then we again generate. So we know that the word we just got is not in the end word because it's never going to be the case based on our constraint. And we start generating individual words. And then we're going to say there's a new word in word set, which is in the ladder here. And this is the approach we'll have. We start with hit. First thing is we're going to queue it here once we find it. And we're going to remove it from the ladder. Because we go from hit to hot, so HO. And now we're at level 2. We're at hot. And from hot, what we find out is we're going to do the same thing. We're going to pop it off. It's hot in the end word. No, it isn't. They're not equal. So we're going to create different iteration. And we're going to be able to create lot. We're going to append it into the queue. Once we create the combination, we know that it's in the word set, which would be the ladder here. And then we're also going to remove it from the ladder. And now we go back to the queue here. And we're going to take out, this is the front, we're going to take out dot. And then through dot, we're going to do again here, we're going to find that dog, which would be G is the only index that we're going to end up changing. And we're going to put it in the queue, which is here, append it, take it out of the ladder. So the ladder ends up removing a word. And then we go back here and we end up finding dog, or lot in this case, because it was at the front of the queue. So then we got lot. We're going to find log, meaning G is where we end up changing T from T. We're going to go to G. We found it here. We're going to append that word to the queue. So that's what we got, log. And we're also going to remove it from the ladder here, the word list that we were given. And then again, dog is in the front. So dog is what we're going to go through. Dog, when we change it, cog is going to be one of the words that we append, which is here. We're going to remove it from the ladder. And then again, we're going to dequeue it because we got lot here. And then once we go from log and we dequeue it, we see is log equal to it. No, it is not. So then we make different type of searches. A new substitution word is in the word set. Yes. So we got cog, and then we'll come back. We'll pop off cog, and then it's cog equals to cog. Yes, it is. So we'll return the level, and that's how that function works. So now, instead of searching from only beginWord to endWord, we're going to search from both directions. So one BFS starts from beginWord, and another BFS starts from endWord. So the search continues until both BFS frontier meet in the middle. This reduces the number of levels explored, making it significantly faster than standard BFS. So here's the BFS standard right now. So when we use BFS, we'll have start. We're using numbers as an example in this case. But BFS would have done the levels here first. And let's say we would have ended up 1, 2. And then this guy would have moved, literally we would have gone 1, 2, possibly 3, 4, 5, 6. Whereas if we were to use bidirectional search, we would have gone 1, 2, and this guy goes 1, 2, and then they meet in the middle. So total step would have been 1, 2, 3, 4. So this makes it much faster than BFS. All right, now that we understand the concept, let's implement bidirectional solution. So here, this is going to stay the same. We're going to still initialize, so we're still going to see if it's in a word set, and we'll return 0. And this is where we're going to make a change. Since we're going bidirectional, now we're going to initialize a hash map. That's going to be beginWord, and then backset hash map is going to be endWord. And we're going to initialize it to level 1, since that's our starting point. We're still going to use the queue. No, actually, we are going to use front set and back set in this case. And then here we're going to say, instead of this, now we're going to say if the length of front set is greater than the length of back set. So if front set is greater than back set, we're going to make front set equal to back set. So this way we always have a shorter sequence to work with. And then we're going to initialize next set to equal a set. So this way we always have unique words that we're adding to it. We're not going to need this here. And we're still going to be doing this portion, but we're going to use for word and front set. So we're going to indent this, different combinations of the word. So we're going to go for in range and word, and we're still going to go through the alphabet, and we're still going to create the different word here. Now inside here, we're going to make a little change. And the change we're going to make here is, we're going to say if new word in backset. And here we're going to return level plus 1. So before, this was outside the while queue. Now we have it inside. Now what we're trying to do is we're trying to show, so we got front set moving in this direction and back set moving in this direction as a way of saying they meet in the middle. And that will make it much faster by doing it this way. Okay, so now that we did that, let's say if new word is in word set, will stay the same. But now, since we initialize next set, this is we're going to change, instead of queue, we're going to use next set, and we're going to use add now. We're going to add the word. So we're just going to add the new word, and we're now going to remove that same word as we did before, because we don't want it to be inside the ladder once we already used up the word, because we don't want to revisit it. So then here, the distinction now is that we're going to have front set is going to equal to next set. And also, we're going to increase the level. So now if we return it, if we find it, we increase the level to show how many steps it took. And if we end up not finding it, we're going to include it in our front set, and we're going to increase the level. So the only distinction here is that we're going to be using two methods. We're going to use a front set and a back set. Back set being the target word, and front set being the starting words. The whole goal is for them to meet in the middle, and this would be much faster. Both accept it, and let's see. So here's 278 seconds, 59, memory's 13 and 7.3. So let's see if it beats if it's faster. And 31 milliseconds is way faster, a little bit more memory efficient. Actually, according it beats 85%, so it's a lot better. Even though it's megabytes is not that big, it's still a lot better. Okay, so again, the previous problem was showing that we were changing the index 0, and it was going to be 8-bit sit, because we're changing for index 0 from A all the way through Z. Again, we're going to go through index 1, and now we're changing index 1, A, B, C, all the way to hot. It is in the ladder, as you can see here, hot. And so it would be similar to the enqueue here, but instead we're going to add it to the set instead of enqueue. Okay, so here's an example walkthrough. We are initializing front set, as you can see here, back set. So front set hit, back set cog, and this is our word list. And then again for iteration 1, we're going to be hit is going to be our front set, back set stays the same. As we change the letters, we'll find a hot. After we change O, it's going to be level 2. Cog does not change in this case. The list doesn't change either. And then we'll go to iteration 3. Now in iteration 3, we're going to add lot to it, because we ended up changing H to L. And also we're going to add dot. Dot was added first, since it's ABCD, and then lot second. So this is at the front of the line. And then what we're finding out here is that length for the code here, length front set is greater than length back set. And since that's the case, we're going to initialize front set with back set, and then we're going to create a new empty set. Then we're going to go through the word, through the front set, which in this case right now is going to be like this. So now cog is the word that we're starting out of. And then we're going to change cog to a different word through our manipulation here. We're going to see if the new word is in back set, which now front set used to be this, and now back set became that when we did the swap. So is a new word here. And then we're going to, again, if we find a new word, we're going to add it to the set. We're going to remove it from the ladder, which is this one. And then we're going to initialize, once we're done with this loop, initialize front set with the new words that we ended up finding out. And that's what we ended up finding out that log, you go from cog here all the way up to log by changing the letter C. Again, front set is smaller, so there's not going to be any swap. So we go to iteration 5. So we go from log all the way to lot. So here we find out that is lot inside the back set. Yes, it is. As you can see, it is inside the back set. That means they met in the middle. So lot is here. So the route we went from hit, hot, and then from cog, log, and lot. So they met in the middle, and therefore we know that we're able to create a combination such that we're able to reach cog. And the combination of bidirectional BFS is both time efficient and space efficient. The time here for the standard BFS is big O of n times L, which is what you see here. And the bidirectional is big O of n divided by 2 times L. N is the number of words in the list, and L is the length of each word. So bidirectional BFS is way faster. And here we're able to show that if we were to use that for searches, it was going to be n factorial. So it was going to take a lot of time, so much so that we couldn't execute in LeetCode. And this right here is us showing you the standard BFS is just going from hit all the way up to cog, whereas bidirectional is going to hit all the way up to lot, and that's where they meet in the middle at lot. I hope this walkthrough helped you understand how to efficiently find the shortest transformation sequence in the word ladder problem using bidirectional BFS. If you found this useful, don't forget to like, subscribe, and hit the notification bell for more in-depth coding tutorial. See you next time.